So, welcome today to this series of lectures on convex optimization, and today we are going to talk about a very important class of convex optimization problems, the linear programming problem. The linear programming, the growth of linear programming had been a phenomenal success story in the history of mathematical optimization. Linear programming came into the scene in the late 40s and dominated much of the scene in mathematical programming, possibly till the mid of 80s, when the interior point methods gave it not only a further boost, but also brought into the foray a lot of other problems which were modeling applications quite much in a much better way than linear programming problem. But the influence and the techniques of linear programming in optimization continues to remain so, and possibly linear programming is one of the single most important aspect of convex optimization which is much well understood. So, that is why we would call this series set of lectures. So, though there is a separate lecture on linear programming in this NPTEL series given by Professor Prabha Sharma. She was my ex colleague, and I just want to let you know that I want to give this lecture not as a repetition of what she had given, rather give you a completely different point of view, more from the point of view of convex optimization rather than the separate point of view one has for linear programming, because linear functions are special class of functions, right. Linear functions are special class of functions, and so for linear programming problems there are separate techniques for solving them. Though we will show one of the major techniques, simplex method would be discussed here, but in an approach which is completely different from the standard approach that you see in the books and literature associated with linear programming, especially at the undergraduate level. Our approach would be more from the point of view of nonlinear optimization, nonlinear convex optimization, and we would see what impact one can have when we bring in those methods to study linear programming. So, we will spend a part of our time discussing linear programming, not the whole of our time. Rather, I would say in optimization there are two approaches, two types of optimization is there. One is continuous optimization, another is discrete or combinatorial optimization. What we had been discussing till now is essentially continuous optimization, and in discrete optimization you have the feasible set could be discrete, but having a large number of points. So, point by point enumeration of the function value becomes very difficult. So, one has to find an easier way to go to the minimum value. So, that makes that subject much more harder. Continuity gives you a lot of ground, because convexity gives you a ground because of its connectedness. If you have a point, you have a neighborhood around it and you can jiggle around that. So, there is a lot of plus point of trying to understand optimization by learning continuous optimization. So, what we are going to do in this set of lectures is to give the continuous optimization point of view of linear programming, though we will talk about simplex method, but it will be from a very different angle. So, but I am sure you will have fun throughout as you learn this part, and that is why I call this series of set of lectures, this specific part for linear programming, as the pleasures of linear programming. So, to start with linear programming, where the objective and constant functions are linear or affine, I would rather go ahead and first start you giving a little bit of idea of what is a linear function, affine function, and then. So, you already have an idea about linear function and affine function, but just to recollect and strengthen your understanding, I would just do that. So, first we start with the definition of a linear function. A function f which takes an element in Rn and places it in R is linear if the following two conditions hold. First one is the condition of additivity, that is vectorically add two elements in Rn, then the functional value at the new element x plus y is same as the functional value of f x added with functional value of y added as real numbers. See, we could define this from Rn to Rn, Rn to Rm does not matter, but we are doing it Rn to R because that is exactly what we are interested in. Second property is so you take any alpha element of R, take any x element of Rn, f of alpha x, if you may take a scalar multiplication of x with alpha, then operate the function, it is same as taking the functional value f x and then multiplying it with alpha. So, this is true for any pair x y in Rn, this is true for any pair alpha, any alpha in Rn, any x in Rn. So, this property is called the additivity property. And this property is called the homogeneity property. Now, it is very important to understand that does this function have a particular representation, is it something much more specific than this sort of definition? You can actually use very basic facts from linear algebra, and I will leave you as a homework. To show that if you give me f, if f is linear, then there exists an A in Rn such that f of x is nothing. So, when you evaluate the functional value f at x is nothing but inner product of this A or dot product of this A with this vector x, which is nothing but a1 x1 plus a2 x2. So, it is a1 x1 plus a2 x2 plus an xn. So, this is the standard definition of dot product which all of you know. Now, then so if it is simple to see that f is a convex function. So, now we come to the definition of an affine function. So, in our definition of affine functions simply means that you have a linear function. So, affine function h x is a linear function f x, which is a times x plus some number b. So, a is in Rn and b is in R. Now, it is very important to note the geometrical picture of this two things, linear and affine function. Let me come to R2. Now, if I look at a function f x is equal to x, function where x is in R, then this represents a linear function. So, the line f x is equal to x is a line through the origin x, and this is your f, sorry. So, this is your origin, so this is your x equal to f x. Now, if I say f x is equal to, so h x equal to f of x plus 2, then you add 2 to all of these, and so the line, whole line gets shifted. So, this is your f x and this is your f x plus 2. This is your f x and this is your f x plus 2. So, this is a linear function and this is an affine function. The linear function always passes through 0. In fact, if f is linear, show that it is homework, but f 0 need not be equal to 0. The f 0 here is 2 for the function f x plus 2, that is this is not, this function is nothing but x plus 2. So, geometrically there is a shift. So, you translate a linear function, you get an affine function. So, now let me write down the very basic or canonical or natural model, I would say, of a linear programming problem. We will give some examples of how, what are linear programming problems. First, let us write down the mathematical thing and then we will try to develop some examples. So, a linear programming problem in the natural form or canonical form. So, linear programming problem in the standard or natural form. Is to minimize C x in a product of C n x, which is also written as C transpose x. C n x are vectors, which is same as C 1 x 1. Of course, C is element of R n and you are minimizing over R n, and thou subject to constraints, following constraints. So, here are my first m inequality constraints, and because usually linear programming comes in applications where the decision variables are non-negative, usually, not always. So, it is quite often standard to have this n additional inequality constraints called the non-negativity restrictions. So, usually by the going by the lingo of linear programming, these are called inequality constraints, and these are called these x 1, x 2, x n, these are called non-negativity restriction. In fact, even if your problem has not got restrictions on the variables, we can still pose them as a problem like this. We will come to this later on. Now, there is an important thing. I can write this thing in a much more compact way. Suppose I consider a matrix whose row is A, first row is A11, A12 dot 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 A1n, and mth row is AM dot 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 AM1 dot 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 AMN. Then they form a matrix, and this can be expressed as a matrix multiplication. Now, so I can write them in a much more compact form. So, I can write this as minimize where A is a M cross N matrix with AI is equal to AI1 AIN as its ith row. So, with I varying from 1 to m. Now, there is an important question. What do I mean by these signs? These signs means component wise greater than or lesser than. So, Ax is a vector taking a vector in Rn to Rm. So, that is why it is a M cross N matrix, and B is an element in Rm. So, this B. Now, what I want to say is that the first component of this vector Ax is less than equal to B1, second component less than B2 and so on, and x1 greater than equal to 0, x2 greater than equal to 0 is written in a compact form, same as writing x is in Rn plus is same as writing this n components greater than 0. So, this is a compact representation. Now, the important question, why you need constraints to define a linear program or linear programming problem? This is sometimes it is usually called LP in the canonical form. So, I will just say LPC. So, why you need constraints to define this problem? Because if you have a linear, just an ordinary constraint problem, ordinary convex problem, say x square, you can obviously minimize over the whole R. But why can't you do it? What happens? Why you need to put these additional things for a linear programming problem? The question is a very simple, and the answer is also simple. The answer is the following: if you look at the function f x equal to x, just do this little experiment. Whichever you go, this way or that way, right? Whichever way you go, if I go make here x go along x towards infinity, my function value becomes larger and larger. If I make x go towards minus infinity, my function value becomes lower and lower. What you can prove, which is again your homework, f x equal to say a x, a element of Rn is unbounded on Rn. So, this is your homework. F x equal to a x is unbounded on Rn. Now, I will show you that you can still write this in a much more simplified way, because if you observe that solving inequalities is a very difficult ball game. It is not so easy to solve inequalities. So, we would rather solve equalities rather than solving inequalities, because equalities are much easier to solve. You know, there is Gaussian elimination and some other techniques by which you can do something. So, now can I write this, at least this part, in the form of equalities? And the answer is yes. So, we go back and try to do that. So, now I can write this as follows. So, this just let me complete the writing, 0 into and then do the following: subject to sorry, this you might not be able to read very clearly, it is A1n, same thing what I had written earlier, this is AMN. Sorry, this would be equal. So, these variables are slack variables. So, in earlier description this was less than equal to B1. So, if I add a non-negative quantity I can make it equal to B1. So, I have x1 bigger than 0 xn bigger than 0, x1 hat bigger than 0, xm hat bigger than equal to 0. So, these variables are called slack variables. More precisely what has happened here is that I have a diagonal matrix which has, I have added a diagonal matrix whose diagonal consists of some non-negative numbers. So, I can write this as minimize Cx subject to Ax plus diagonal matrix. When you write a diagonal matrix you do not write the whole matrix and write the diagonal and put the zeros on the side, but you just write what is there in the diagonal, because it is understood that everything else is 0, every other element is a 0 entry. An x hat, where x hat consists of the vector now this greater than equal to 0 is a comparison in Rm and this greater than equal to 0 is a comparison in Rn. So, we can write it much more fully as follows. We can write this as so, you see I have converted a problem into an inequality form. So, this from an inequality form to an equality form, at least in the main part of the constraints. See, these constraints are usually called in the literature as soft constraints for reasons which would become clear later on in the course, and these are called hard constraints which are which we cannot avoid in some sense. It is very difficult to replace these constraints. Here some sort of penalization can be done, some sort of way we can take off this constraint and put it in the objective, but these constraints are not so easy to take off, as we have seen while we constructed the Lagrangian functions. We had never touched these constraints, we have touched these constraints which are called the soft constraints. We have never touched the hard constraints. You can touch the hard constraint, but the whole thing becomes much more complex. So, it is much more easier to just take the hard constraints separately and work with them. Now, this leads to what is called linear programming problem in the standard form. This to minimize C transpose X this is a standard thing where C is in Rn and A is a M cross N matrix. So, let us give an example of such a problem where naturally a linear programming problem arises. So, this would as an example we will show the transportation problem. This is quite interesting because it is a real life thing. So, you must be quite happy that too much of math is now gone, but and you are doing with real stuff, but you will soon see the math coming back in as fast as possible, because you can't really do the stuff without math. You to have a deeper understanding of things in science, you need to have a good understanding of mathematics. Now, here I have a series of m supply points, supply of certain goods. So, these are warehouses storing books. So, these are say Flipkart warehouses, because everybody buys from Flipkart nowadays, and these are the demand points, right. So, this is storehouses and this is the point where there is a demand for Flipkart books from Flipkart or any other thing. So, there are n such points. So, this is a supply point, these are the warehouses of Flipkart, and this is the demand point, these are cities, say this is supplying to. So, this is the thing, and this is the Flipkart self delivery points. So, there are n points and the m warehouses, and now from each one of them I can send to any one of these destinations. So, if I ask, hey, if I am say if this is Kanpur, then when I order for a Flipkart thing, the demand, when I make a demand, it will check wherever the supply is there, and it will see from where it can in the least cost send me the material. So, from any supply point I can go to any point. For that there is a cost involved. So, go from C1 to 1, I have C1 1. So, 1 to 2 I have C1 2, 1 to n I have C1 n. Similarly, for the second point C2 1, these are the cost involved transferring from this Flipkart warehouse to a supply point C1 n, so and so forth. You can do for the others also. For the m also you can have, it is CM1, CM2 and CMN. So, this is something like a transportation network. These are transportation network. Now, if this is the case, then I do something. Let us proceed. Now, every warehouse has some amount of say books or any other materials. This warehouse is A1, this has A2, this has A3, and there is certain amount of demand from each of these places. So, the demand is B1, B2, Bn, sorry, this is Am. A very important assumption that we will take in modeling, because when we model we need to take assumptions. Any mathematical model cannot just capture real life just like that, because reality is quite complex. So, you do have some simplifying assumptions, and by getting some results from that simplifying assumption, you can have probably quite a good understanding of what is actually going on. So, I would now go ahead and take this demand supply condition, which says that the demand must equal the supply. It says that the total supply that you have in all the warehouses must match the demand, and that is then we can actually start distributing, match the demand that you have so this we say T total, this is equal, this is called the demand supply condition, this is inherent. So, if you do not have this balancing equation, then some other you can still get back to this form of work by putting some additional variables, but this is a standard thing that we assume. Now, what is our intention? Our intention is very simple. We want that okay, this Cij, the cost from going from I to j, so how much material I should carry over the whole network, so that my total shipping cost is minimum. So, when Flipkart is doing a self delivery, it is not going through some other customers, because nowadays Flipkart self delivery has increased, because why? Because they have observed that if they do, they can using the self delivery process deliver you the material at a much cheaper cost. And so, the total cost over transporting so many goods over the network is minimum. So, that is our goal. Now, the Cij could be greater than equal to 0, could be even negative. So, the cost of shipping a quantity element Xij. So, if I ship the amount of material Xij is shipped from I to j, then the cost is, so this is cost of going from I to j, it is a unit cost, and a cost of say courier cost of one material, then which we say is standard. So, then the cost is our goal is to minimize my transportation cost. So, the goal is so, the problem now is to minimize subject to. Now, if I fix my ith supply point and vary my jth supply point, the total goods that I can send from my ith supply point is Ai, which is equal to the total amount of supply that I have. I cannot send anything more. And total goods, so if I keep my jth reception point fixed, then whatever the amount of material that I need from total material that I need from the various supply points as I vary it over supply points must equal my demand, and that is exactly what is required. And all of these quantities Xij's has to be greater than equal to 0, which is quite natural because there are some books or something like that. What you get is a linear programming problem. This is called the transportation problem. So, you see how very important mathematical real life problem has been mathematically modeled as a linear programming problem. Isn't this beautiful? It shows the power that is inherent in this whole subject. Now, we have already learnt a bit about duality when in the last lecture, where we tried to find the dual of a linear programming problem, last lecture in the standard form. So, we are not going to get into dual aspects at this moment, but we will now show that you can actually take a very simple problem in the natural form, and then if you have just two variables and two constants or three constants, then using geometry you can very well figure out how to find the minimum. But for that we will come in 2-3 steps. But first thing we have to determine that the problem of linear programming problem is actually a convex problem. So, I have minimized. So, I go back to my standard form, LP in the standard form, which that would be always marked as LP, not LPC. I am not writing what is A, what is B and all those things, this is not required. Now, this set C, the feasible set, consists of all x in Rn which satisfy your homework would be to prove that C is a convex set. So, what you conclude is that LP is a convex problem. But it is very important to note that this class of set C is a very special kind of convex sets, which we had already mentioned once, called polyhedral convex sets. So, the set C is a polyhedral convex set, means it is a intersection of finite number of hyperplanes and half spaces. It means it looks like something like this, something this part, forgetting out this. So, something like this, say a set like this or a set like this. These are some examples of polyhedral convex sets. So, this is a polyhedral convex set. Can you figure this out? Can you figure out why? So, definition of a polyhedral convex set, as I recall, that is in the intersection of finite number of half spaces. Now, in order for you to understand how do we figure out the minimum of a linear programming problem, you must understand the notion of the direction of descent, that is, in which direction I will move so that my function value decreases. So, this is something would be important. So, we do not have much time to discuss the direction of descent today. So, what we will do is we will postpone it for the next class, but what we will do is that our idea would be to solve out this particular problem in a geometrical fashion. Many of you would say, okay, we have read this in our undergraduate days, those who are already undergraduates watching this program, graduate students, but there are a lot of things which you have not really understood when you did the undergraduate classes. So, we would like to make certain things clear rather than mechanically show you what happens. We would like to tell you what the hell is actually going on beyond this set of rules. What is the math. So, direction of descent is a very important thing, that is, in which direction, if I have Cx, this problem is C transpose x, in which direction I should move in Rn, so that my functional value will continue to decrease, because I want to minimize the function. So, I will end here with giving you a homework. Draw the feasible set of this problem. So, we will come back and start tomorrow considering a problem of this form: minimize f x, x to minimize it over the whole R n, and f is a differentiable function. You know by this time what is the meaning of a differentiable function, we have already discussed it. So, for this, so in which, suppose I have a point where the function is not minimized, that is the gradient of f at x at that point is not 0, then I need to move towards another point where the function value actually decreases. So, I am actually going towards the minimum. So, minimum or local minimum. So, that is, so how do I know which direction to choose? The direction along which I get this decrease of function value is called the direction of descent, and like it is coming down a mountain basically. So, we will start our discussion with the direction of descent tomorrow. Thank you very much.